So welcome back. Now I want to next present to you the design of our particular solution, TamiFlex, solution for resolving reflective chords. TamiFlex, first of all, it's available as an open source project in our GitHub account. I encourage you to take a look on your own. What's important is that it basically comprises three components, namely these two and this one here. And two of them can be applied before the actual static analysis that you're running. And then one is actually running also after. And yeah, there are these play out, booster, and play in components. And I want to go through them now one by one. First of all, step one, play out. So TamiFlex is a toolchain that allows you to deal with both reflection and custom class loading, in particular in this case for Java applications. And yeah, it consists of this play out and play in agent. And these two components, they're basically mirroring each other's functionality, you could say. The task of the play out agent is to lock all reflective chords at runtime into a log file. So that means this is not a static approach, it's really a dynamic approach. We run the actual application that we seek to analyze. And during runtime, we capture all the reflective chords that are happening, and we simply log this into a file. Using this particular information from the log file, then in the next step, the static analysis can use that information to create a better, sort of more correct chord graph, right? So it will in particular incorporate all of the different reflective chords that have been recorded in the file. And the solution that we have implemented in TamiFlex, it works reliably for Java applications. It does not work though for Android applications, unfortunately, because we build on top of some low-time instrumentation APIs that are simply not supported by the Android or Dalvik virtual machine. They are exclusively supported by Java virtual machines, but they're actually by multiple ones. So the most popular Java VM is probably Hotspot, but there's also J9 by IBM, and there are others. And they all support this API that we're using. So you can use TamiFlex in combination with all of these virtual machines as well. Let me show you a relatively simple example. So this is an example I've adopted from a previous one I showed you. So here we're using a reflective method call to actually obtain a handle to method foo on an object, well, first of all, from class A, okay? And then we're invoking this also on an object that has type A. And we're invoking it a couple of times, but that actually doesn't really matter. But now the idea is that we execute this program and we trace what is happening, okay? And this is basically how it works and what kind of output you will see. So first of all, we call Java main, so we run this main class here, but we have an additional command line parameter, which is enabling this playout agent. And here we are telling it to place its output into this out folder, okay? And then you would see some logging output, and in particular, it will tell you that the log file has been written to disk to this particular file handle here. And if we output this, you will see that we will see, or that we have recorded a call to foo within class main inner class A, okay? But then also another call to foo within main.b, okay? Why is that? You would see that the first invocation here will actually invoke this method on A, which is of type A. But then, interestingly, obviously also a contrived example. This method call here will replace that same variable A or its contents by an object of type B. Okay? And therefore, when now this invocation is done again on A, this handle here will no longer point to an object of type capital A, but of an object of type B. And therefore, we see this particular call target here. And we also record, as you can see here, using line number information from the class files, at which line number this particular call was issued. So we know that this call was actually at line 11 and the other one at line 12. So we have the kind of call. So this is now method invoke. We are also capturing class for name and so on. Then we also have the target of the call, and we have the location of the call as well. Now the static analysis, it will use this information as follows. So first of all, if you were to run suit with its Spark call graph engine on this particular class, analyzing this class main, you wouldn't really see a lot, right? So you would see calls to the initializer here, to the constructor. You would see calls to class get method. You would maybe see still a call to method.invoke, but that's it, right? And in particular, Spark would not know how to resolve these particular calls here. Now, we have implemented an extended version of Spark that is able to parse these logging files here and make sense of them. And so it will take a look at this and actually incorporate this into its call graph. And in particular here, it will figure out that we are actually instantiating these different types of objects here. And then we are also calling, in particular, these foo methods on these particular objects of these types. And we are also calling the constructor of B here within a.foo, for instance, right? And so this would actually then give us a completely correct and sound call graph for this example. And for this example, it's simple, right? Because there's only a single simple straight line execution of this program, right? There's only a single execution path. So in particular, the selection of these different reflective calls, it's independent of the command line parameter that we choose for the application. So you can do a single dynamic run and you record all the different reflective calls that there are, and that gives you a complete picture of the analyzed application. In this example, I will show you other examples where this is more complex. So the algorithm for call graph extension, it's really rather simple. So basically, when processing a call statement S that is calling invoke and within some method M, right? So we have a method M that contains a method.invoke call. Then if the log file contains an entry for that particular statement, so matched by the line number, then for all recorded targets T of S that are part of the log file, insert a call edge from S to T, okay? And I told you we use the line number to do this matching. In some cases, we might be unlucky that we have a binary that does not have line numbers. Then we still try to do some matching based on the surrounding method M. That's why this is important. And also on the type of statement. So for instance, if there's only a single method invoke statement within a given method, which is usually very likely, then we can still uniquely identify that statement. So the playout agent, it's essentially a logger component, and I want to show you how this works. So first of all, the setup here, we have a program that is using a particular class loader to actually load classes, for instance, from a jar file or from some other external location. And then this class loader, it's being hooked up with a playout agent. And this is something that's really facilitated by this dynamic instrumentation API in Java. And so the way this works is that the program, for instance, asks the class loader to load some class, for instance, main, and then this will be returned to the class loader. But before this is actually being returned, it will be passed to the playout agent, right? So this is basically bypassed. And the playout agent now has the opportunity to actually instrument this class. So it can add additional statements to the class. And in our case, we will add these logging statements. So basically at the place where normally this application would simply invoke method.invoke, it will now invoke additional functionality that actually implements the logging. This is called load time instrumentation. Now then this class is actually passed to the program and it's being instantiated and run. So it's executed. And then this also means if we now load additional classes such as Java lang reflect method, then this is being returned as well, is instrumented as well. Yeah, then you see this additional instrumentation here that we have inserted into this class. And yeah, that then basically causes the particular code to actually be written to disk. So when we have a call to method.invoke, then this particular call will actually, well, it will create the file handle and will add the logging and actually write this to disk. And there are different ways to implement this kind of logging. The way we have implemented it, the actual instrumentation, it's actually restricted to classes of the logging API itself. So we will we'll instrument the class method. We will instrument the class. We will also instrument the class constructor. And depending on your configuration, maybe a few other reflection API classes, but we won't really instrument anything else, in particular, nothing else within your program. That's not that important, but it makes the instrumentation relatively efficient. There still is some overhead. I will still be talking about this, but it could be worse. So in the end, you basically have these instrumented classes, method, constructor, and class, and they all have these logging points at which they write particular log entries to disk. And yeah, this log is then being used by the static analysis, like I showed you. Now, is this a general solution? No, it's not, right? But it's some solution. So the static analysis can use information from the log file to create an at least mostly complete call graph, right? Or let's say more complete call graph. But the obvious problem is the call graph is only sound for the recorded program runs. So that means you do get some guarantee. The guarantee is if you have exercised a certain set of program runs during the playout phase, then you are guaranteed that the static analysis gives you sound results with respect to these particular program runs. Okay, so it basically goes back to a sort of testing approach, right? But if there are runs that you didn't cover, in particular if there are parts of your programs that you didn't cover, your static analyzer might still miss things. So the question is, how many runs does one actually need to record? One hypothesis is that often some few program runs suffice to actually trigger and record then all reflective calls that a program can possibly trigger. Okay, that's a hypothesis. It may be false, but we did some experiments to actually figure out whether this hypothesis holds or not. And I will still be talking about this. Before I get to this though, I want to explain how we deal with another important and interesting problem, namely custom class loaders. to conduct a static program analysis, we need to know the whole program's code, right? At least if it's an interprocedural or even a demand-driven analysis, even, I mean, you know, if the analysis is demand-driven, you probably don't need the whole code, but we still need all the code that matters. And at least, you know, if this contains generated code and custom class loaders and so on, this might still be a problem. So the question is, what if code is loaded from what I call obscure locations, right? So locations we don't really know much about, from which we can't easily inspect classes. So, you know, it could just be loaded from a flat jar file. That's then maybe not that hard to deal with, right? So you could just load the class file itself. But we have seen situations where there are nested jar files, so that's basically not a standardized Java format anymore. Then people are using a customized class loader to sort of unpack the outer jar file and access the contents within the inner jar files. That's impossible to deal with in general, because then the static analyzer would need to understand these custom class loaders. You may have other situations where code is even loaded from the internet, and maybe at static analysis time you don't have internet access. You know, then what do you do? Or there can be even yet harder situation where the program generates code at runtime, so it doesn't even exist at analysis time at all, even based on some runtime arguments, right? Then out of luck doing this statically, right? So that's impossible. We observed that this is not so much a problem in Android, because back then, at least, pretty much all the Android jars were packaged into a single APK file. Although I actually have to say this changed in the last 10 years. So in particular, when you look at malware, it now tries to use dynamic loading pretty comprehensively to actually also obfuscate what it's doing. But even some goodware Android apps, they use dynamic loading to some extent. Not all of them, but some of them. And in Java, so basically desktop or server-side Java applications, this is definitely a big problem, because it's a very frequently used feature. And back then we were actually motivated by a benchmark suite that was very popular, or still is very popular, when it comes to benchmarking static analysis applications. So, you know, when we or others implement a new static analyzer, for instance, based on Suite, but also based on some other static analysis engine, often we are interested in knowing how well does this analysis perform on some real-world programs. And Da Capo is a benchmark, so it's a composition of some real-world programs. And you can download it, and in this version back then, it was all contained in a single jar file, which is nice, because then you can just run it using a certain command line like you see here. So here we are selecting the given benchmark FOP, and then this jar file is just run. It's just executed with this FOP benchmark, and you can simply read off how long it took. Okay. Now the problem is, though, if you look into the packaging, then it's not a flat jar file, but you have this one jar file that has its jar directory, and then here there are a lot of different jar files for all the different benchmarks and their different dependencies. And this is a non-standard packaging structure, and in order to load the right benchmark for the right command line here, Da Capo is basically implementing some class loading magic. So it has a customized class loader that's part of its implementation here, and that then, you know, accesses the right jar files for the right benchmark. But obviously the static analyzer, you know, it can't understand, or at least it would be pretty much impossible, right, to make it understand this Da Capo class loader here, right? How should it make sense of this? I mean, this is the class loader itself. It's a Turing complete program. So we really have no chance to really figure out what exactly it's doing. So the way we then thought we would deal with this, and this actually seems to work, is we would do a trick. Namely, during playout, we actually don't just record the reflective method calls, but we also record all the classes that the program loads on this particular program run. And then we simply take these classes and we dump them to disk into a flat directory in the form of simple class files. So that means we could run, for instance, the little main program that we had earlier using the playout agent, using actually the same command line that I showed you earlier. And then you will see that in this out directory, we don't just have the logging file, but we actually also have all the different class files that the Java virtual machine loaded into itself while this particular program, this main program here, was running. And you will see that actually there are many more classes than just main, right? This is because, of course, you also have the Java standard API, and this is fairly huge. And even if you're not using a lot of functionality in a little main class, it's actually a fact that there are more than, I think, a couple of thousand classes loaded by the Java virtual machine. And because they're all loaded, we will write all of them to disk, actually. And then the static analysis can simply analyze the program from this out directory, right? So we now have a guarantee that all the classes that matter, at least for this particular program run, for this input, they are contained in this directory. And we also have the information from the logging file. And that's really all that the static analyzer needs to do its job. That's how playout works. In the next video, I will then talk about another interesting component that helped us generalize the approach, and this is called boosting.